The developing nervous system is subdivided into subpopulations of progenitors or neural stem cells, and each subpopulation gives rise to specific subtypes of neurons and glial cells. And so pMN is one of those subtypes of progenitors that produces motor neurons, which are responsible for controlling all of our motor functions, and oligodendrocytes, which are a glial cell that produces the myelin in the central nervous system. So a long-standing problem is how a common population of neural progenitors or neural stem cells can make these two very different types of cell types. And motor neurons and oligodendrocytes are completely different. So how does that work? And so people have wondered about this for years and years and years and years. The model always has been that any one individual pMN stem cell can produce both cell types, although the evidence for that has never been very strong. And so our work over the past few years has revealed that, in fact, that they don't come from the motor neurons and oligodendrocytes don't come from the same progenitor cell, but they come from distinct progenitor cells in a way that gives us the impression that they're actually a common progenitor cell. And that's because what we hadn't appreciated before is that there's tremendous cell movement within the nervous system. Our previous conception had been that it's a very static structure, that cells remain pretty much where they are born in terms of building the early spinal cord, and that progenitors are not moving long distances. But by using time-lapse imaging in zebrafish embryos, what we found was that progenitors can leave one progenitor subdomain and enter another subdomain. And so that accounts for this production of these two different cell types from an apparently common. One of the goals of MS researchers is to try to understand how to replace oligodendrocytes that are lost in MS, resulting in a loss of myelin. And so you can imagine taking stem cells, induced pluripotent stem cells, and in a dish, and directing those to make oligodendrocytes that you could then transplant into a patient and restore some myelination. To be able to do that, you have to know how to direct those stem cells into the myelination pathway. And so that means knowing what the molecular cues are that can direct that process. Therefore, it's very important to understand that very basic mechanisms that operate in development to direct those cells to one fate or another.